Hello, my name's Adam Goss. I just want to take you through some videos of my application running that I've done for my final year project. I'll start you off with the first version here. As we load up, we get the menu screen. This is the first version that I felt was usable for testing. As you can see here, you can navigate through the menu using arrow keys. If you press the Enter key, at the moment it takes you into a submenu, and you can see that it transitions through there. And you can go back and it'll perform the same transition throughout the whole menu system. So the idea is once this is finished, you'll be able to navigate through all of these options, and you'll be able to enter the different modes. So if we enter a game here, you can see the game world. I'm just currently using the A and D keys to rotate left and right, and you can use R and F to toggle the camera angle up and down. So you can aim around where you want to make your shot. The three lines you can see act as a guide. The aiming works down the center of the camera. I can also hold T down and it'll give you a top-down view of the table to give you a better overview of where all the balls are positioned. So once you've lined up your shot and you want to take a shot, just pressing the spacebar brings up the power meter here. This can be adjusted using the up and down arrow keys. So if you want to make a particularly hard shot, you can put it all the way up to the maximum, or you can judge that for yourself. Once you've decided and you're happy with your shot, you press the spacebar again and that takes the shot. As you can see here, the cue ball has collided with the pack and all the balls have responded and moved away. At the moment, this version of the game is running on the particle physics engine, so all of the balls are acting as point masses. The collision detection here is being used using the rays which you can see from the cue ball. The collision detection system operates on finding the time at which a collision should occur within the time frame, and that way it will generate a collision and update the balls up to that point. So therefore this avoids any problems with penetration between the balls. So in effect you get the same sort of result as when you would in real life. The collision occurs at the exact point of contact. At the moment there's no geometry on the table, so when a ball bounces off the cushion, it's not actually colliding with the table. Instead, the cue ball, when it gets to the position on the table, it will instead just adjust the position so that it's on the table and not penetrating the cushions, and then it reflects the velocity of the cue ball. For the pockets, that's a little bit more complicated because of the very basic version of collision detection I'm using for the tables. The pockets need to have an exception rule. So when a ball is within the vicinity of the pocket, as you can see there, it ignores the normal collision detection rules and allows the ball to pass towards the pocket. If I hit the cue ball at, say, the corner of the pocket here, it will bounce. But you can see slightly, if you look carefully, that there is some penetration and it's not quite accurate. I show you here as well, the ball there has gone through the table because of the inaccuracies. Now it's popped back into view. If I show you this camera, it's popped back into view because it's gone beyond the point where the collision detection is being ignored, and then it realised that it's off the table, so it's moved it back. All the collision detection is being performed only on balls that are moving, so all of these balls are stored in a list, and whenever one of them is moving, it will be checked with the other balls on the table to see if it's colliding with any of them. So it does the initial ray check, and it's only if the ray collides with another object, it will then say, will that happen within this time period? Now this is done by measuring the distance between the ball that you're checking and when it would collide with the other ball, or the intersection point of the ray. Now if the length of that vector is the same as the time frame, then obviously a collision is going to occur during that time frame. So then you check and find out when the actual time would have been. So this is the simplest version of the game, and as you can see it does work fairly well, but there are the issues with potting the balls, and it's still only using the particle physics engine. Another little issue I want to show you as well, because it's using the ray collision detection, there's a bug in the way that it's calculating it. So if I hit this really thin, that shouldn't have, the yellow ball there should not have moved as far as it did, because it should have just been glancing past. But as you can see, it acts as if it's taken a full impact, and you can see a similar sort of thing there as well. So I'll just close down this application and open up the next version. Again, it's the same menu system, so we can just navigate through and into a game. I'm going to show you the snooker here, and you can see there's different versions of the games set up, so you've got a different ball set up here. Another thing you can obviously notice is these wireframe objects around the table. And what I've done here is added separate collision geometry for the table itself. So you can see blue boxes. If I just move the cue ball closer to the cushion here, you can see that there's a bounding box around the cushion to act as the cushion, and then for the rounded knuckles at the end I've used spheres here. You see it doesn't quite fit, but what it does give you is much more accurate and realistic collisions, and when it's moving that fast you tend not to see it. You can also see the pink sphere inside the pocket, and so what I've done here, instead of saying is the ball within a certain point to check whether it's been potted or not, it now checks whether the ball itself is intersecting that sphere. So as you saw the yellow ball there, when it got towards the pocket, it will have been intersecting that pink sphere in the bottom corner, and that will have said, okay, this ball has been potted, so it can be removed from the table. So this gives you a much more improved version of the collision detection with the table, certainly. If I hit this knuckle here, the cue ball will angle back like that instead of just coming back normally. This gives you a much more realistic version of play. So you can still pot the balls. It's still using the same particle physics engine, but the improvement here is that the table geometry has been added. But still, I've got the same problem that I mentioned earlier with the rays, so the collisions are not working properly. So the next version of the game, which I'll show you now, has solved that issue by reverting back to the original idea I had, which is just using sphere intersections. So now when you play the game this time, it will check during each frame whether the spheres of the balls are intersecting. Now the reason I avoided this initially and went for the ray detection system was because of interpenetration. During a time frame, the cue ball might have actually appeared and gone through a ball that it hits. So to avoid this problem, I thought using the rays and finding the exact time that it collides and only updating it to that point would be better. Instead, now what I do is I check that it's interpenetrating, and then I will move the ball back along the line it was originally travelling until it's no longer inside the other ball, and then also resolve the collision. So you can see now, using that, if I hit this really thin, it didn't move as far as a full impact. Now, one of the original problems with using just sphere intersection testing is that if you hit a ball particularly hard and it might travel so fast that it will move through the ball and the collision would not be picked up. To avoid this, I've added a multiple time step solution. What this does is add in a multiple update cycle within the normal game logic. So for updating the physics, it takes the time step and divides it into 4 smaller time steps and only updates the cue ball or the moving balls along the shorter time step, so it moves less each update, and then it will perform a collision check. If there's no, and then it will resolve any collisions then, and then it will move on and perform the next update until all 4 updates have reached the max time of the existing time step, and then the rest of the game proceeds as normal. So what this gives you, it gives you the advantage of the correct type of contact being made with the balls, and the penetration is resolved using the collision resolver, and you're not getting the balls travelling through because you're using such small time steps that it's not possible with the speed that you can actually hit the ball for it to travel through the other balls. The final version that I want to show you is the version that is in the current edition of the game, which uses the rigid body physics. As you can see here on the cue ball, I've added some stripe strips so you can see the rotations as the ball moves. And the problem with the rigid body system is there are some bugs which have been unable to resolve so far. At the moment that looks normal, it spins. Okay, you see there it's hit the cushion and it's stuck there. This is one of the issues which I've not been able to resolve so far. This is most likely down to a problem with the collision resolution process, which I've not been able to isolate at the moment. Another thing you might not have seen initially there, but if I play it again, you see the cue ball start to stretch. You can see it's become slightly distorted here. This effect gets worse depending on the rounding errors. You can see there it's gone really bad, and it's gone very distorted here rather than a normal sphere. At the moment also you'll notice that the cue ball has now left the bed of the table. This is due to friction when it contacted with the other balls, and at the moment there is no gravity in place in the system to bring it back down. If you looked at any balls in a snooker game or a pool game at really slow motion, you notice that the balls do tend to bounce quite a lot. As you can see here is a perfect example of how distorted the ball has become. It's become virtually flat and angled. This seems to be a problem with the quaternions. The quaternion is representing the orientation of the ball. You can see at the top here there's some numbers which I'm outputting, which are the values for the quaternions. Because the quaternions are using floating points, there are a lot of errors associated with floating points because they're not always 100% accurate in the computer. And also you have to perform a lot of normalization steps on the quaternions whenever you adjust them. This normalization step is a complex process using the square root, and therefore is not always being resolved. So this is the major issue. I believe the rotation is working correctly in terms of the code, but obviously graphically it's causing a significant issue. This is something I've been unable to resolve and which I have documented in my report.